Okay, so today is the last topic of our course, and it is a really modern thing. So I learned about this in early 90s and from the authors of this. So it is I don't know how to call it, as topic changes the name all the time. So I keep to the most expressive name, black noise. No, I know quite well the authors of this. Leadership and so on. Then they were joined by, say, Watanabe, and some other authors. The idea of this is follows. We are in a good position to formulate this idea. So let us start from the beginning. We introduced a timeline T. It is a set of K delta T, where K is infinite number, and N, and delta T equals 1 over N. It is all non-standard, and consider at every K we introduce its own coin tossing. So a random event with outputs 0 or 1, or I prefer -1 and 1. Yes? So we have Zk is in this set, and they are independent with probability 1/2. So just coin tossing, and consider the full phase space omega is say -1, 1 to the power t, the set of all z0, z n -1. The set of all such independent plus minus ones. And omega is element of this probability, of this space. It's still not probability space. Now, omega is a star finite set. So formally it is like finite set. And so we introduce the algebra of internal subsets of omega. Omega. Now, in particular, omega itself is element of this algebra. Now, in this algebra, I can define the counting measure. If A is a set of our algebra, yes, then we define mu of A equals the number of elements in this set A divided by the number of elements in the whole omega. The number of elements is defined as star continuation of the number of elements in a finite set. Yeah. So this is a counting measure. And now there is a great theory of logic which I told previously, measure space. So we can extend this algebra A, which is just algebra, it is not sigma-algebra. We can extend it to sigma-algebra L of A, complete sigma-additive algebra mu L sigma-additive measure on L of A. Yeah, complete means that contains all null sets, the space of exterior measure 0. That's it. So this is a huge algebra. So we have, after all, this space omega L of A and mu L. It's continuation. So they are now considered as external sets, not internal, as external. So like really like sets in set theoretical sense, L of A is algebra of some subsets of omega. Now they are not supposed to all to be internal. And mu L, it is the standard measure taking values in the standard numbers. So it is because we define for if, say, A in initial algebra, then mu L of A is a standard part of mu of A. So we started from this standard measure, standard valued measure, and then we extended it from A to L of A, it is extension of a sigma additive algebra. And here we found, no, in fact, Loeb found that it is possible by the general Kara-Theodori theorem. So we have this great thing, but in applications we usually use not this full algebra, but some sub-algebras of it to construct interesting and useful objects and theories. So let me remind you. Let us consider the following functions. S AB of omega equals some AN less than K less than BN Zn of omega, and this multiplied by 1 over n square root of n. So this is a function.
Is it Zn or Zk?
Excuse me?
Is it Zn or Zk?
Zk, thank you. Yes. So this is a function which is defined initially on the yes, this function defined in the on the set omega for almost all omega. Now we consider the function, we have to consider standard function of standard of this part SAB of omega. Standard part, it is a standard function, and I denoted it by psi AB of omega. So for different A and B, A and B between 0 and 1, we have this function. It is a function on omega, or in other language, random variables. And consider the sets C, A, B of omega less or equal than C. Yeah. Let us denote the set A, B, C. And this set is in L of A. And consider, these are some specific sets, and these sets define a sigma subalgebra. So we take sigma algebra generated by these sets. So we take all the sets which can be obtained from these sets by countable number of unions and intersections and differences, plus the null sets. And so the sets A, B, C generate a sigma subalgebra which I denoted by W. W is subalgebra of this L of A. So we have one sigma subalgebra, and if you have sigma subalgebra and you have the measure, the same counting measure on this sigma subalgebra, then we have what is called, one moment. The triple omega W and mu L, it is the same combination of counting measure, is called white noise. No. So for any segment we have white noise. No, in fact, white noise is in fact the increment of the linear process of Brownian motion. So we write W of T omega equals C 0 T of omega. This is one of possible definitions of the linear process. And from this definition, we can derive all the properties of linear process. So last time I derived the property that it is a Gaussian process and established its distribution of its value at any time, up to some finite calculations, and that it is with probability 1, its trajectories are continuous. Then there is an interesting book of Edward Nelson, which is called Radically Elementary Probability Theory, where he takes equivalent definition and derives the basic properties of the linear process from this definition. Again, equivalent definition. Okay, so today I wanted to consider different process, which is principally different from this. So we define different sub-algebra and obtain a different process. So unlike this process which is called white noise, that process is what is called black noise. I think it is mostly the I don't know, emotional title, so something which is opposite to white, so has nothing to do with white. So let me start from a simple finite picture. So consider a tree which I would call how it's called? It is a tree such that at every node it is branching into 3 branches. let me draw a picture. These are the nodes of the these nodes are at different levels. So it's level number 0, this is level number 1, this is level number 2, and so on. And at last will be some level number n. So we have this. Now let us play the following game. At every node at the level number n, we write either +1 or -1, or simply plus or minus. Yeah, no, randomly and independently. Plus, plus, minus, and so on. Minus, plus, plus. No, something like this. Yeah, independent. Every time we toss a coin. Now, if you have, if you move to the previous level, n-1, we put here the sign which is the sign which has majority at the previous lower level. So here we have plus, plus, minus. So we have here 2 pluses and 1 minus. So here we write plus. Here we have minus, plus, plus. Again we write plus. If here we have minus, plus, minus, here we write minus. Here minus, minus, plus, we write minus. Here plus, minus, plus, we write plus. And here we have plus and 2 minuses. So here we put minus. Yeah? So this is now if you start here from completely independent pluses or minuses and go by steps, then you will fill all the nodes with pluses or minuses. And now we can let us denote this graph by Gn, gamma n. Let me see how it is done. Now we start from this. Let us denote this pluses or minus by zk. 1 minus 1 and k from 1 to 3 to the power n, because every time the number of the nodes triples. Okay? So we take these variables, and this function, as soon as we fill all the places here, we automatically can fill all the previous places. Yeah? So let us denote omega n is the set of or z k So omega in omega n. So we write zk equal zk of omega. So let us denote the random random argument by omega as usual. Now, if you consider these values of plus or minus in these nodes, they after all denote they depend on the values here, and values here depend on omega. So we introduce the function phi jm of omega. It is the value plus minus the vertex to the level m. Yeah. No, for example, here we have phi 0, 0 of omega. Yeah. This is phi 0, just 1, 0, 1. It is phi 1, 1 of omega, and so on. Okay, so we define in this finite probability space omega, yes, and introduce the counting measure in this omega n. So the number of element of omega n is all these combinations is 3 to the power n. Yeah, all possible combinations of pluses or minuses. And so mu n of A equals again number elements of A, number of elements of omega n. So this way we defined a finite probability space, and you see already we have the following possibility. Here we have plus and minus ones. It is long, no, for n large it is very long sequence, finite but very long. By the way, the natural structure of this end of the set of these endpoints at the level n is approximate counter set, but not usual dyadic counter set, by triadic. Yeah. So we take the segment, then we replace it by 3 segments. Then we replace each of them by 3 smaller segments, and so on. So intersection of all these sets, if you take for all n, is the triadic counter set, because here we have also all these branches lead to something set, to some set which is in this segment. Then if you go, say, along the left branch, so all further points, further ways lead us to the points of this set, and so on. And now let us extend our universe, take a non-standard extension, and extend all these objects. We have a sequence of graphs, sequence of finite space, sequence of these functions, sequence of these functions, and all this can be sequence of these measures. All these sequences are can be extended by as internal sequences to infinite n. So n, omega n, phi, jm, what else? Mu n, and so on, are star finite. So now these functions phi j m, yeah, phi j m. Here m is the number of the level, so level was 0. M less than n, but n in star n minus n, so it is infinite non-standard number, and j 3 to the power n. Yeah. So we have this. And each of these variables takes the values plus 1 or minus 1. Yeah? So we have the sets A, J, M, plus the set of omega in omega n such that phi jm of omega equals 1, or here plus 1, and a jm sets omega in omega n such that phi jm of omega equals minus 1. So this is also some family of sets which generate after all sub-algebra of the algebra of all internal sets. These sets are also internal. So this set internal. A, J, M plus minus generate an algebra. B. Sub-algebra of A. Yes, no, it's relatively small sub-algebra. B. Okay, so then we can define omega L of B mu L. It is the Lloyd algebra defined by B. So what is this? There are some sigma unions of elements of B, and we add also null sets, add or subtract, so that it is again a sigma algebra, a standard sigma algebra. Now mu L takes standard values. Yeah? So it's standard sigma algebra, which is responsible for such infinite construction. So it looks like follows. You can draw a picture. So we have this tree. We have different levels and so on. Let me show you this. And here we have a level number n, but n is infinite. Let me write this. Yes? And here we have we should extend the real line so that it can hold a corresponding very large set, and this very large set, which is, let me denote it also by T, and very large set, so the number of element of Tn equals 3 to the power n. Here we, at every element of this set, we define plus or minus 1 independently and with probability 1/2 each. And then we propagate this to all the nodes of this graph. And we regard what we see in this graph, so we should know something about these values plus or minus 1s. So we measure some quantities which are extracted from this and have some conclusions about this function, sequence zk, which describes the plus or minuses here on this line. So they can be called observables. Yeah? In the case of white noise, observables were the sums of elements on different different segments from A to B. Yeah? This is observables. Here we don't have access to these properties, to these functions, but we have access to the values of plus minus 1s here. Yeah? So I would say that the difference between this construction and construction of the white noise is the set of observables. Here we have one set of observables, there we have other set of observables. We see different things. Yeah? Now, this example was created, I think, just to show the simplest and the most accessible example of such a process which has nothing to do with the with white noise. So I don't think that we should look for some, say, other sense in this example. But the sense is great. I want to compare this example. So, 1 moment. So, we have the triple omega W mu L. It is white noise. And omega B mu L, let us call this system voting. Because at every level we vote, and at the next level we have those who has majority of votes. So it is called voting, voting model. So here we have what's important, algebra of some events which we can observe, yes, event. Here we have also some events, yes. So the question is, what is maybe a relation between these two algebras? And the answer is no relation. Yes? So the theorem is that any event A in W is independent of any event say B in B. So they are orthogonal. What does mean independent? This means that a probability A and B, measure of intersection of A and B equals mu A of A, mu L of B. Yeah? And this means that if you know anything about this function z or k, anything which can be measured in here in this algebra, it gives us absolutely no information on what will be the result, say, and back. So if, say, we know that in this 3, here we have plus, yes, so the winner of this multi-step elections is plus, yes, it says nothing about the votes on the lower level. Yeah. No, when I was at high school, we had interesting problem about multi-step elections. So multi-step elections is elections where first we define small districts and has elections in this district. Then you take the groups of these districts, yes, and the election goes among the winners of the elections in the smallest district. Then you group this larger into the still larger districts and continue this process n times until at the last stage you have say several very large districts and winners of there, and then among them we take the majority, and this will be the president. And the question was the following. If we know that only 1% of population is going to vote for current president, but this president can organize the process of election, I mean this partition in the sub-district, districts and so on, as he wishes. Can he win? Yes, the answer is yes.
They do.
So we can. So in particular, in this model, this means that we can start from the function such that percentage of pluses here is say less than 1%. Yes, and no, after all, at the top will be plus. Yeah. So arithmetical majority has does not have any weight, and the structure has maximum. Yeah? So I wanted to explain this theory. What happens here? I wanted to reformulate it. Here we are talking about the sets, measurable sets, and I wanted to talk about measurable function. So function is measurable if its set where it is less than any given C is measurable, belongs to respective algebra. So suppose that F is W measurable, G is B measurable, and integral F the mu L is 0 is integral G the mu L. So we can integrate with respect to of their common measure mu L, because if a function is measurable with respect to subalgebra, it will be measurable with respect to the whole algebra. Then integral Fg d mu L also is 0. So I would say the space of the functions which satisfy these, which are W measurable with mean value 0, and the space of the function which are B measurable with average 0 are mutually orthogonal. No, I have to say that it is square integrable, so that this integral converges, of course. I wanted to choose one element from here and other element from here, yes, from this space, because it shows the grand idea. And then for any other element, it is done the same or similar way. So let us take f of omega equals 1 over square root of n sum zk of omega. So it is what we had in the definition of the white noise, but we take it sum from k from 1 to n. The sum of all these pluses or minuses. Yeah? And g of omega equals phi 0, 0 of omega. Yes, it is what we have here in the upper node. So after we start here at the level n, which is in fact infinitely deep, and fill all the places here, we reach this node, the upper node, and here we have either +1 or -1. And this depends on what was here on the ground. And this is a function, another function. This function is in interior function, so it is measurable and it's bounded because it takes values ±1, so everything is fine. This function f is also integrable, and because we know already that its values have Gaussian distribution, it is in L2. Okay, now how can we show it? Yes. How can we show it? Let us consider first what happens near the upper level, upper node. So suppose we have this situation that at the upper node we have plus. So we have what can be in the lower node. All in all, we have here 3 nodes beyond, below this, and 2 outcomes in each. So all in all, we have 8, 2 to 3, it is 8 possibilities. So possibilities are the following. Plus, 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 minus, plus, minus, plus, minus, plus, plus. It is 4 possibilities, and then there are other possibilities. Minus, plus, minus, minus, plus, minus, plus, minus, plus, minus, minus, and minus, minus, minus. So here we have plus, here we have plus, here we have plus, here we have plus, here we have minus, 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 and minus. Now let us introduce Q plus of M. It is a number of pluses at the level M. Q minus of M, number of minuses at the level M. Yeah. And now I want to make some simple computations. These signs here are random and independent. They are random, it is sure. Why they are independent? Because, say, this minus comes from, we continue this branch down till the ground, and it will never intersect with this branch. Yeah? So it depends only on some segment here, which is not intersecting with segment which affects this sign. Yeah? So they are independent. Yeah? And therefore, I wanted to find a conditional average of Q plus of 1 condition, but U plus of 0 equals 1. Yeah. So what is conditional average? We have take this condition, we have consider all situation, these 4 situations when we have 1 on the top, and find this, and this happens with the same probability. So we have to take the sum of the classes, here the number of the classes in the string, here, here, and here, and here, add and divide by 4. So here we have 3 and 6, 9 classes divided by 4. So it is 9 over 4. And E of Q plus of 1 conditioned by Q plus of 0 is 0. Yeah? So how many pluses are here? We have here 1, 2, 3 pluses and 4 possibilities which are defined by this condition. So we have 3, 4. Now, similarly, yes, and now we have to write similarly, E of Q minus of 1 conditions Q plus of 0 equals 1. So how many minuses here? Here we have 1, 2, 3 minuses. And divide by 4 is 3 over 4. And E of Q minus of 1 conditions by Q plus of 0 is 0. It is this case. So here we have 9 minuses. Divided by 4 is 9 divided by 4. Now I wanted to take what I am more interested, Q average of the following quantity, Q plus of 1 minus Q minus of 1 conditioned by Q plus of 1 is 1. So in this case, we have to subtract this, take this minus this, it is 6 over 4 or 3 over 2. And E Q plus of 1 minus q minus of 1 conditioned by u minus of 1 is 1. No, we have to consider this. So here we have q plus is 3 over 4, q minus is 9 over 4, so it is minus 3 over 4. Now we can repeat this for the next level. Yes? Repeat here for the next level, and then, no, you know, I can a little wave my hands, but let me write the answer here. Average of u plus of n plus 1 minus q minus of n plus 1 okay, condition that q plus of 0 is 1 equals second e u plus of n minus q minus of n conditioned by q plus of 0 is 1. So every time it is multiplied by 3 seconds. And so this means that this average of q plus of n minus q minus of n conditioned with q plus of 0 is 1 equals 3 seconds to the power n. Yeah. So it is positive. So some trace of this event that at the top is plus, some trace remains. But now we see that this trace is really relatively negligible. So our function f of omega, what is this? No, it is g of omega. G of omega equals, in fact, and the number of the nodes below it is 3 to the power n. 3 minus n over 2. And now we have to take exactly this difference, q plus of n minus q minus of n. Yeah? Because where is plus, we have to take plus, add 1, where is minus, we have to subtract 1. So we have exactly this. Equals 3 minus n over 2. What we have? Yes, here it is. And Fn f of omega f of omega is the following function. It is plus 1 where there is sign in the upper node is plus, and minus 1 if the sign is minus, equals 1/2 chi where phi 0, 0 is 1 plus 1 minus chi of omega equals minus 1. Yeah? So, where this, it is the function which defined in the whole phase space. So then, integral fg d mu L over omega. No, we can express it through these quantities. Equals, so we have to integrate this function over first over the set where this is positive, so it is this q plus is 1, and then minus integrated along this where it is minus 1. So as a result we have, it is 1/2 3 minus n over 2, and here we have e q plus of n minus q minus of n q plus of 0 is 1 minus e q plus of n minus q minus of n, conditions q plus of 0 is 0. Yes? Why 1/2? Because this set where it is 0 and this set where it is 1 are transformed to one another by changing plus to minus and minus to plus. So there is this isometry, and so the measure is 1/2. Equals 3 minus n over 2 average of q n minus q plus of n minus q minus of n, conditioned by q plus of 0 is 1. And what is this? We know it is equals, let me write it here. It is equal 3 minus n over 2 times 3 to the power n equal square root of 3 divided by 2 to the power n. What is this? Equals 0 866 and so on to the power n. Yeah? Now we have to take a standard part of this. Yeah? So n is an infinite number, infinite non-standard number. So this means that it is 0. Yes? So we found that this integral is 0, scalar product is 0. So these two vectors are mutually orthogonal. Now, we found that the quantity C 0, 1 of omega and is, say, orthogonal to phi 0, 0 of omega. Yeah. So C 0, 1 of omega is 1 random variable. Phi 0, 0 of omega it is this is plus or minus 1 on the top. Yeah. Now we can do the same for C AB of omega and phi Jn of omega. Yes. It will be repetition with small changes. Yeah. So, but this function, namely this function, all this function, CA beta, AB of omega, generate the sigma algebra W. Yes? So if you take the sets where these functions for different A and B are less than some C, yes, then these sets, if you take span sigma algebra on them, we get sigma algebra W. These generate sigma algebra B. Yeah? So W, and this generate sigma algebra B. Okay, so we have a dense set of elements of the space, which is defined, Hilbert space is defined by these functions, yes? Here dense space and Hilbert space defined by this function. No, I mean Hilbert space which are measurable, or functions which are measurable and have zero average. And so this means that these two subspaces of the full space of square integral function and A are orthogonal. Yeah, so it is the best way to say that these two processes have nothing to do with one another. Okay. No. I'm sorry, what time is it?
5:30.
How much?
5:30.
5:30. Do you mind maybe 15, 20 minutes more? Because I wanted to say a few more words.
For me, I can.
Huh?
For me, I can. I have to catch the last bus.
Okay.
Like my house is really far.
Okay, so anyway, you'll see it in the morning. Yes, do there exist more, I would say, closer to life examples of such exotic processes. So why it is a process? It is a process because we have a corresponding sigma subalgebra, a corresponding measure or system of measures, and so it is genuine process, not worse than white noise. But can we have some perceivable process? Yes, we can. I give you a couple of examples, more physical, which are derived from this voting model. So one example is the following. Consider a vertical pipe and consider a chain of small drops. So this pipe is filled by a viscous liquid, and we have some small drops which are moving down this pipe. The drops are formed by liquid which is heavier, has more specific weight. So the speed of the drop is defined by its mass. Yeah. So V equals C times m to the power 1/3. It is why 1/3? No, it is a famous result of Stokes. So a small drop or small ball goes down in viscous fluid with a velocity which is proportional to its radius. Radius is mass to the power 1/3. Now, if a larger speed reaches the smaller, larger drop reaches the smaller drop, then they immediately coalesce and form one drop. So these drops are always coalescing, and so as time goes, we'll have more heavier but less numerous drops. Yeah. So all this process, as I described it, is defined by the initial positions and masses of the drops. The number of these drops and the number of these drops per unit length goes down. The average mass grows, and so it is already not void problem to find the law of this growth of average mass, and it is a model of real problems. Now we can continue this. Here we have the masses which are finite, small but finite, the distances which are small but finite. So we can say extend our universe, including this liquid with drops, to a non-standard universe, and consider infinitesimally small drops and infinitesimally small distances between them. Yes? And then we start this process from there. So this. So what is our initial, say, universal sigma-algebra? In fact, what is our initial conditions here? It is positions and masses of these drops. Yeah. So we have to know. For example, we can choose these drops, their masses and distance between them, random and independent initially. However, they immediately become dependent, of course. And it is a deep probabilistic problem how to describe it. And then what are the observables here. Observables are positions and masses of these big drops after finite time. Yeah? No, the first theorem in this theory is that for any positive time, we have, if even we start from infinitesimal drops, after any positive time, we have just finite number of them. Yeah. So this is one example. Other example is the following. Consider the following situation, just physical situation. We have a long fence with a horizontal upper limb, and we have a long rope. And the rope is put on this fence. Fence is, just a minute, the fence is horizontal. So it forms the loops. And so on. This is the piece of the rope which appears from our side of the fence. This is the piece which is other side of the fence. Yeah? Now what happens? If you neglect the friction, then you see this loop is short and this is long. So this is heavier, and so this loop will overweight this loop. So this loop will elongate, and this loop will shorten. After this loop will disappear, you have the sum of these two loops. So after a while, you have this picture, yes? No, and then it will be released, go down, and so on. And then after all, we'll have a longer loop here. But here we have this longer loop from that side and shorter from this side. So after all, these two loops will coalesce, and this will become on the other side. Yeah. So we see again this successive coarsening of this picture. Yeah. Now, mathematically, to some extent, it can be described by the following differential equation. d2u dt square equals d2u dx square plus sine of u. Yeah. So we have this x. We have some function, yeah, and this forces sine of u is positive for positive u and negative for negative. So it is pulling these parts which is positive up, and this part is pulling down. And now what is stronger? If this part is shorter, then this will overcome. If this is shorter, this will overcome, and so on. So, again, we'll see the picture which is the coarser and coarser, yes? No, it's interesting to evaluate some quantities. For example, the number of zeros of this solution, yeah? Or, say, integral u xt square dx. Yes, the average integral, it will grow. How fast it will grow, and so on. And again, it is a natural idea to push this process down to the situation when these loops are infinitesimal. So we have infinitely many zeros and infinitesimally small distances between them, so it will be something very fast oscillating, yes, and then it will develop according to this equation, and we'll have this picture where these sizes of this loop looks will change. So it is another process. So what is the process in fact? The process is this infinitesimally small oscillations, infinitely fast, infinitesimally small for t equals 0. It's an initial value. So the thing which in the usual world cannot be noticed and measured. But here we cannot measure it itself, but we can measure this function when it becomes large, no, at least positive. Yeah. So our observables are something like this, or something like the number of zeros here, and there is again the same situation. And certainly this no, it is not explored completely, but here we can hope that, say, the infinitesimal average of this initial condition doesn't have something to do with this with behavior at large time. I think not. It is like with the voting, because all these examples are variants of voting. Here they vote with their weight. Okay, I had some other examples, but maybe let us keep them for another course. Thank you.